In part A of this lecture, I went through and we derived the Green-Saint Venant strain tensor. In this part B, we're going to try to make some sense or understand the meaning of the Green-Saint Venant strain tensor. We're going to start off taking a look at a picture that I have pulled up from a previous slide, and this was the body in its original configuration. We have points A and points P in there in region R, three-dimensional body, and we have ds, which is the distance between those 2 points. We also wrote on there, we didn't talk too much about it at the time, but we also wrote on this picture a unit vector that goes from P to A, and we said its components were N1, N2, and N3. Let's look at that just a little bit more. You can write it as a column vector like this. And it's set up in such a way that its magnitude is equal to 1. And it has to be a magnitude of 1 type vector. Well, let's write this in terms of what we have already on this page in these red symbols. Well, the vector in between A and P we call ds with a little line under it, and we said we could write that as dx1 e hat 1, dx2 e hat 2, and dx3 e hat 3. So the dx1, dx2, dx3 are the components of the vector. So we can say that in the index notation with the free index I, that the components of that vector are dxi. Well, the magnitude of ds with a line under it, that vector, we said was what we had in red, the ds. So if we want a unit vector that points from P to A, that would be what we're calling our n. Our unit vector n would be ds vector divided by the magnitude of ds vector, or ds vector divided by ds, the scalar distance, or we could say that the components ni are equal to dxi divided by ds. We're going to write this just a little bit differently. We're going to write this for dx, and we're going to say that dxi is equal to ni ds, that scalar magnitude. Okay. So we have this unit vector now. And so for the change in the square of the lengths, in the previous lecture we had ds squared minus script s squared minus d regular s squared is equal to 2. What we call the Green-Saint Venant strain tensor epsilon ij, dxi and dxj. Both of which now we can write in terms of the unit vector n. So we're going to write this as 2 epsilon ij ni ds nj ds. And right now ni and nj are both the same vector. They're both pointing from P to A. Let's make a little note of that up here. Alright, well, let me make a little bit of room. And we're going to do a little bit of manipulations on the far left side of this equation and the far right side. On the far left side, I'm just going to write it down, d script s squared minus ds squared. And we're going to group some terms. So we have 2 epsilon ij ni nj ds squared, since we have 2 of these terms. And we're going to isolate the epsilon ij, ni, and j. So on the left-hand side, I'm going to have a 1/2 d script s squared minus d regular s squared divided by d script s squared. And then on the right-hand side, then I have epsilon ij in I and nj. Now, I think maybe it's easier to see now why epsilon ij is unitless. We have length terms squared on the top and on the bottom of the left-hand side. Obviously, the left-hand side is unitless. And so, therefore, the right-hand side must be unitless as well. And the ni and the nj, these are unitless vectors. So the epsilon ij is a unitless term. It's a unitless quantity. All right, let's do a little bit more algebraic manipulation with this left-hand side. Leave a little more space. I'm going to divide both of these terms by d regular s squared. And that first term I'm going to write as the ratio of d script s divided by d regular s, that quantity squared. And then obviously what's left on the second term, that's just 1. And then over here on the right-hand side, then I have epsilon ij in I and nj. Well, this term that we have right here has a special name our book likes to use. Not everybody uses this, but it's going to be convenient for us to base our discussions on strain with. And this term is called the magnification factor. And I'm going to abbreviate that as MF. Now that term doesn't look like it makes a whole lot of sense right now, but we'll get a better feel for it here very soon. So we'll call that just the magnification factor. But inside of that magnification factor term is this ratio of d script s by ds. And that is a term that we're going to call the magnification ratio. So if you recall our other figure that goes along with the one in the top left-hand corner, as we deformed and distorted that body, the distance between point A and point B changed. They both got mapped into their script P and their script A, and we had a d script s for the new distance. So the d script s by ds, that magnification ratio, just represents the ratio of that line segment length in the new coordinate system, or the deformed body, as compared to the length in the original body. And this thing could be rotated and spun around however it is. If we can identify where those 2 points land, we can find d script s. If we know where they started, we can find d regular s. So that ratio again is the magnification ratio. All right, well let's try to make sense of all of this. I'm going to look at a special case that I'll write down here in just a moment. So let's consider a special case. I find it's often useful to look at some of the special cases to get a little insight into things. But a special case of a deformation where the object has been deformed is the case where the object has not been deformed. And so d script s would be equal to d regular s. Maybe the object's been rotated in space, but the line segment has not changed length. This would be a rigid deformation. So in this case, the magnification ratio would be equal to 1. And if the magnification ratio is equal to 1, then the magnification factor would be equal to 0. Now, what's significant about that is that if we have a scalar quantity of 0 on the left-hand side being equal to the tensor epsilon ij times a vector in I and a vector in j, and recall that n is not the 0 vector. Can't be. It has to be a unit vector. The only way that we can get 0 on the left-hand side is if epsilon ij is equal to 0. Okay, so in this particular case, with a rigid translation, say, no change in line segment length, a magnification ratio of 1 gives a magnification factor of 0. That means that we don't have any entries in our strain tensor. Now we can arrange this strain tensor just like a matrix, a 3 by 3 matrix with epsilon 1, 1, and so forth. So the components of that matrix would be equal to 0. So that's kind of a nice special case to think about. A case where we don't have any strain at all. And it makes sense. All right, now let's take a look at our magnification factor again with another example. Okay, let's do something maybe a little bit more interesting. Say in our body, we had points A and P over here, and its length in between was 2 units. And after it's been deformed, it goes into its final configuration. Maybe it's over here somewhere, and it ends up with 10 units. Okay, so this would be d regular s, and this would be d script s. Now our magnification ratio in this case would be equal to 5. And we can find our magnification factor by taking 1/2 5 squared minus 1. And let's see, 25 minus 1 is 24. 24 divided by 2 is 12. So our magnification factor in this case is 12. Okay, so there's an example with some numbers in it. And maybe it still doesn't make a whole lot of sense. So let's do another example where we have a special direction for our n vector. All right, so we're going to consider the special direction equal to 1, 0, 0. So it's solely in the x1 direction, whatever direction that points. Let's see if we can get an interpretation of this. Now again, we're using both of these being the same vector. I'll give you a hint coming up. We're going to take a look at shearing strains very soon, in which case those two n unit vectors are going to be different vectors. Right, but right now we're going to take both of them the same. It's equal to 1, 0, 0. So our magnification factor, we said, was equal to epsilon ij and I in j. Now we can write this out by our index notation using our double summation. But let me show you how you can do this pretty quickly using matrix notation. So we have a matrix of strain components. It is symmetric. I'm going to write it as if it is not symmetric, but it is symmetric. We have all these terms in here. 3 by 3 matrix of components. And then we have our vector, n1, n2, and n3. It's a unit vector, and it's not equal to the 0 vector. And the operation that we're doing here is this vector times this matrix dotted with this vector again, the exact same components. So if we look at our special case where n is equal to 1, 0, 0, I'll write all this out again. I won't always write all these terms out, but I think it's useful to think of it this way. And I'll tell you, sometimes it's much easier on a quiz or an exam to write all of these out in a matrix format than it would be to write them in an expansion of the index notation. Okay, so let's take a look at just the first part of this. We have a column vector 1, 0, 0 multiplied by our 3 by 3 matrix of components representing the strain tensor. What we get in that case is a vector that has these components. And now we're going to take that vector and dot it with our unit vector again. And what we get then is simply one term in this expression, epsilon 1, 1. Now we could look at other unit vectors, and that would involve other components, and it's just not going to be convenient for the discussion we're going to have, so we're going to look at a few different cases of one-dimensional stretching. Okay, so let's keep this in mind for just a moment. Okay, so we have the special case that the magnification factor is equal to epsilon 1, 1. When our unit vector is equal to 1, 0, 0. And the reason why we're going to take a look at it is we're going to take a look at two cases. We're going to take a look at a rubber strip that starts out a certain length, say 40 millimeters. And it gets deformed, and it gets really, really long. I'm not even going to draw it as long as it really gets. I've tested rubber strips. Good fresh rubber can really be stretched out before it breaks, and this is pretty typical. It has a final length of 400 millimeters. So we can take a look at our magnification factor. In this case, we've got 1/2 d script s by ds quantity squared. So we have 400 divided by 40. That quantity minus 1, and the whole thing divided by 2. And that would be equal to this strain term, epsilon 1, 1. And if we put that in here, we have a half. We got 10 squared minus 1. So that's 99 divided by 2. We end up with 49.5. Okay, so that's a pretty interesting strain value. What does it mean? Well, maybe it doesn't mean a whole lot, but let's put that in context. One of the things that you've probably done in your first class in stress analysis is engineering strain. So the definition of engineering strain, we're going to call that little e in our class. It's the change in length divided by the initial length of some body. Now in this case, this would be, the change in length would be 400 minus 40 divided by the original length of 40. So 360 divided by 40, that has an engineering strain of 9. Okay, so from a percentage point of view, it increased in length by 900%. Okay, so we have this kind of difference here between this thing that we're calling the Green-St. Venant strain tensor. We got a 49.5 for that component, and here for our engineering strain we got 9. Again, that doesn't seem to make a whole lot of sense, but it does illustrate the difference when we have finite deformation as opposed to what we usually deal with for most metals, very small amounts of deformation in the material. Well, let's look at this special case again, but now instead of looking at a rubber strip, let's take a look at steel. We're still looking at the special case where we have only our unit vector 1, 0, 0. But say we have a steel bar that starts out with a gauge length of 10 millimeters. So that's our D regular S. And it stretches out a little bit. typical for metals, it doesn't change very much. It's measurable. Maybe it changes length and increases to 10.01 millimeters. We can calculate our magnification ratio if you want. 10.01 divided by 10. Well, that's hardly much different than 1. It's 1.001. Let's calculate our engineering strain. In this case, it's 10.01 minus 10.0 divided by 10.0. In this case, it's 1,000 microstrain. That's a pretty good level of strain in a steel. We're probably not yielding it yet, but if we get 3 or 4 times that amount, we very well could be yielding that metal, depending on what its yield strength is. Now let's look at the magnification factor. So we would have 1/2 the magnification ratio squared minus 1. And that would be what we would call the term epsilon 1,1 for this special unit direction case. And if we compute that, we would get 1,001 microstrain. So look at that. When we have small deformations, the idea that we've developed for the Green-St. Venant strain tensor, that component is pretty much the same as what we had for the engineering strain definition. A little bit of difference, but 1 microstrain out of 1,000, that's within the accuracy of most measurements. Okay, so what should you use? We have lots of different strain ideas floating around right now. We have this magnification factor thing. Sometimes it turns out to be epsilon 1,1. Sometimes it may not be if we use different directions. We have engineering strain that we have right here. What do we use? Well, obviously the important thing to note is that what we use and how we interpret it will depend very much on whether we have small deformations or finite deformation, continuum mechanics, or finite deformation elasticity. Those large deformations will make a big difference in how the strain is interpreted. All right, let's keep going with this just a little bit. We can talk about some other measures of strain as well. Let's look at something kind of like a rubber strip. Let's look at a rubber band. And on this rubber band, I can mark some different spacings. And I'm going to try to get this approximately equal spacings here. They got bunched up a little bit more towards the bottom, but you kind of get the idea. And I'm going to take this rubber band sitting over here. Let's see if I can do this. It's going to stretch all sides. Let me see if I can stretch just one edge of this. And there's my stretched out rubber band. So if I put my x-axis going down the length of the rubber band, remember we have that special case where the unit vector is equal to 1, 0, 0. Then the magnification factor is equal to epsilon 1, 1. If I take a look at a special case where the distance in between these spacings, I can call this distance d1, and the final distance here d2, that's our ds and our d script s that we had previously. If I have a uniform elongation, the displacements will look something like this. If this is point A and this is point script A over here, then the displacement of A will be equal to a constant times the x distance. The x, or you can call it x1 if you'd like. Okay, so it has a linear displacement field. So if the bar is uniformly stretched, we get a linear displacement field. And this term alpha is a constant. Alright, so we had this magnification factor term equal to epsilon 1, 1. If we want our magnification ratio, that magnification ratio then would be equal to alpha. And we're not thinking about any other displacement fields. We're not thinking about any kind of contraction in the 2 direction or the 3 direction. So our displacement field components, u1 would be equal to alpha x1, u2 would be equal to 0, and u3 equal to 0. Now in reality we will get some Poisson type contraction, but we're assuming no change in thickness. I'm going to keep things easy for right now. Okay, now we know how to compute the magnification factor if we want it, and we'll do that pretty soon. But let's take a look at this term epsilon 1, 1. We haven't looked at this in terms of partial derivatives of the displacement fields yet. But in general, we said that epsilon 1, 1 is 1/2 partial derivative of u1 with respect to x1. We wrote all these down previously. Partial derivative of u1 with respect to x1 again, plus 3 other terms that come right here. Partial of u1 with respect to x1, partial of u1 with respect to x1, plus partial of u2 with respect to x1, partial of u2 with respect to x1, plus partial of u3 with respect to x1, and a partial of u3 with respect to x1. We can simplify this quite a bit, because if we look at the u2 and u3 displacement components, those are equal to 0. So this term and this term and that term and that term go to 0 just by looking at those partial derivatives. And what we have then here is epsilon 1, 1 is equal to 1/2. Then we have 2 of these same terms. So what I'm going to do is I'm going to take that 2 and distribute it into the 1/2, and it's going to be equal to the partial derivative of u1 with respect to x1 plus 1/2. Then what we have left here is partial of u1 with respect to x1 quantity squared. Well, let's look at the partial derivative of u1 with respect to x1. That is equal to the term alpha. So the way I have it here is epsilon 1, 1 is equal to alpha plus 1/2 alpha squared. Let's take a look at this in a little bit more detail. Let me make some room. All right, let's look at our engineering strain again. So it was the change in length divided by the initial length. So in our example here, the initial length was equal to distance d1. The final length is equal to distance d2. Since it changes linearly, this is a factor times d1 on this fixed end right here. Okay, so I'm looking at this like it's fixed on this side. So d2 is equal to this factor alpha times d1. And then we can have our change in length divided by our initial length. So this would be on top d2 minus d1 for d1. So this would be our engineering strain alpha d1 minus d1 over d1. This would be equal to alpha minus 1 times d1 over d1. The engineering strain here then would be equal to alpha minus 1 in this particular case. All right, so for example, again, if alpha is equal to some very small amount of number above 1, okay, then epsilon 1, 1 is pretty much equal to alpha and here our engineering strain would be equal to this alpha minus 1 term. Actually, I have a little mistake here that I need to sort out, and it has to do with my final dimension. And I wrote this wrong on the previous page. I'll have to try to correct that as well. If I get a chance, I'll reshoot this video. But the final length isn't what I've just written down here. Let's think this through for a moment. The final length will be equal to d2, but it's going to be equal to the starting position plus the displacement. And if the displacement looks like alpha times x, then this would be equal to alpha times d1. So this term right here isn't alpha times d1. This term for the engineering strain is equal to 1 plus alpha times d1. And so when I combine those terms together, the d1s will cancel out. This term is not alpha minus 1. This term is just alpha. All right, so if alpha is a very small quantity, let's not use 1.01. Let's use something very much smaller than that. If alpha is something like 0.1, okay, so 0.1, if I square that and divide it by 2, that's 0.005. And if I add that to 0.1, 0.1 is actually kind of a big number for this. If I add that to 0.1, then epsilon 1, 1 will be equal to 0, 0 0.105. And the engineering strain then would be equal to alpha, which is about 0.1, which is 0.1. So in this case, for small alpha, our green St. Venant term is approximately equal to our engineering strain term. So in more general terms, then, we can say that this magnification factor, which was this alpha plus 1/2 alpha squared, in relation to the engineering strain, which is the E, magnification factor can be written as E, because that's alpha, plus 1/2 E squared. And this magnification factor is a large deformation strain measure. And the E is a small deformation strain measure. And magnification factor then would be equal to the engineering strain. The engineering strain is small. And lastly, to wrap this up, there are other strain measures that we can use as well, such as logarithmic strain, which is often used in larger deformation measures, and other strain measures too. Again, to emphasize, there are many different ways to characterize strain, but it always has something to do with deformation and the amount of deformation, and how that's all wrapped up and what you might use it for is going to depend a lot on your context. All right, so that'll wrap up this second part of the lecture on the green St. Venant strain tensor. We're going to continue on with the next lecture, looking more in detail at shearing strains, taking a look at the derivation of that and then what it means.